Hi guys! The first lesson that we're going to be doing is exponential growth and decay functions. You'll see here that an exponential function is represented as y equals a times b to the x minus h power plus k. A couple important things. A cannot equal 0. If a equals 0, then we just have a line, because all of this stuff would go away. Alright. B, our b value, the one with the exponent, has to be greater than 0. So this b right there has to be greater than 0, which means it has to be positive. And it will also not equal 1. Alright, let's look at some of the characteristics of exponential growth and decay functions. The domain. The domain is a set of all real numbers. So one way to notate that is with the r. Remember, we're always going to do negative infinity to positive infinity. Alright, my infinities are really ugly. Sorry. Negative infinity to, those are worse. You get the idea. Negative infinity to positive infinity. The k value is a horizontal asymptote of the graph. What's a horizontal asymptote? That, and I've kind of talked about that in class a little bit, but it's a line that the graph is going to approach, but it's never going to touch it, it's never going to cross it. So when we're graphing, you'll see that I will always make the asymptote look like a dotted line, and then when I'm graphing, you'll see that the graph is going to get really close to it, but it's never going to touch it. It's almost like the graph is attracted to that asymptote. Alright, the range. Remember, the range is how wide the graph is. So the range is either going to be y is greater than our k value. Here's our k value. If a is positive, this value here. So it would look something like this. The range would be k to infinity. If the a value is negative, so again we're going back and looking at that a value, if it's negative, then the range will be less than k. And we did this not too long ago when we were graphing our square root and cube root functions. So then we would just write negative infinity to k. Alright, the y-intercept, we're always going to look for that by plugging in 0 for x. If you plug in 0 for x, it is going to end up being our a value. And again, I'm going to do that when we're working with the parent functions and we're going to be shifting graphs. Alright, let's try some. Alright, we're going to start with an exponential growth problem. An exponential growth is going to happen when the b value is greater than 1. Remember, it will never equal 1, because if it's equal to 1, then you just have a line again. Alright, so as long as that number with the exponent is bigger than 1, it's going to be a growth. And I've got two examples here. You will see, if you look, it looks like the graph is kind of flattening out. So these lines I'm drawing right now are asymptotes. And what we're going to really look at is the right side of the graph. So check out the right side of the graph here. Check out the right side of the graph here. Notice that those right sides are going away from the asymptote. So you might want to add a little note to your notes. The right side is going to go away from the asymptote. Okay, so that should say ASY. The right side goes away from the asymptote. That means it's going to be a growth. On the other hand, if you look at decay, you'll notice that the b value, the number that has the exponent, is going to be a fraction. I mean, I can't always say it's a fraction, but that b value is between 0 and 1. Here would be the asymptote right here. It's the line where the graph is approaching. And again, look at the right side of the graph. The right side of the graph is getting really close to the asymptote. Again, maybe add a note. The right side is going to get really close to the asymptote. That's how you can tell the difference between a growth and decay just by looking at the graph. Alright, now let's back up and go ahead and look at domain, range, and the asymptote. The domain is, for all of these, it's going to go to the left forever and to the right forever. There are no numbers that you can plug into an exponent that won't work. Remember, our domain issues are fractions, the denominator can't equal 0, and radicals. We don't have either one here. So the domain is going to be negative infinity to positive infinity for all of these. So negative infinity to positive infinity. Alright, so I just filled in all the domains. I know my infinities look kind of funny. Sorry about that. Okay, I'm going to skip the range for a minute and I'm going to look at the asymptote. So the asymptote on all of these are going to be y equals 0. And the way that we're going to figure out what the asymptote is you're going to look at your k value, the one that's been added on. And nothing's been added here, actually, to any of these. So the asymptote on all of these is y equals 0. Alright, the range gets a little trickier. To figure out what the range is, you're going to have to look at your a value. If your a value is positive, the range will start at the asymptote, and then it's going to approach infinity. Now, notice, I am not including 0 because it can't actually touch the asymptote. I always kind of joke, can't touch the assy. So if you touch the asymptote, you're going to have issues. So we will not have a closed bracket here, we will just have a parenthesis. So no closed bracket because it's not included. Alright, look at the a value for your next problem. It's negative. Look at your graph. Do you see how it's under the x-axis? Since it's negative and it's under the x-axis, that means that it's the smallest y value, how low it goes, is negative infinity, and it's going to approach or get really close to the asymptote. That'll be its biggest. So again, if a is positive, it's going to be the asymptote to infinity. If a is negative, it's going to be negative infinity to the asymptote, or your k value. Alright, so look at your decays. The first one is positive, so it's going to start at your k value, which is 0, because there wasn't anything there, and then it goes to infinity. Alright, I don't have room to write this. On the last example here, a is negative, so it's going to start at negative infinity, and it's going to approach k. Remember, k is plus 0. Same thing as your asymptote. Alright, let's actually try some more problems here. Alright, we need to determine if each of these functions is representing a growth or a decay. So what you're going to look at is your b value. B is always the number that has the exponent. So in this first one, it's 0.5. 0.5 is between 0 and 1, so that makes this decay. The domain is always going to be negative infinity to infinity. Next, I'm going to find the asymptote. I like to find the asymptote before I do the range. So you see that the k value is 2, so the asymptote is going to be y equals 2. It's going to be a horizontal line at 2. Now the range is going to have 2 in it. It's just we need to figure out if it's 2 to infinity or negative infinity to 2. Look at your a value. Your a value is positive. Since it's positive, it means it's going to be above my asymptote. So the lowest point will be 2, and then it will go up forever. Let's get another one. Start with your b value. That's 5. It's greater than 1, so that's going to make this a growth. The domain, again, is negative infinity to infinity. Let's focus on the asymptote. If you look, there is nothing added after this. The k value is 0, so my asymptote is y equals 0. To figure out the range, look at your a value. Your a value is negative, which means that it's going to be below the asymptote. So it's going to go down forever, and then the highest point is going to be 0. But it's not going to include it, that's why we use parentheses. Alright, last example here. Please be careful. Notice that there is a negative exponent. A negative exponent means that we're going to flip our fraction. So let me see if I can fit this in here. Alright, so I rewrote it. Y equals 3/4 to the positive x minus 4. So if it would have stayed a 4/3, then it would have been a growth. But now that it's 3/4, that's smaller than 1, so this is a decay. And the domain is negative infinity to infinity. The asymptote. You look at the number that has been added or subtracted outside. You see a -4, so my asymptote is going to be at y equals -4. Range deals with the a value. There's actually a 1 in front that we don't really write. It's a positive 1, so that means that my range will start at -4 and it's going to be above it, so it's going to go all the way up to infinity. Let's look at some graphs. The first graph here. First we need to figure out if it's growth or decay. The number with an exponent is 3. It's bigger than 1, so this is growth. That means that the right side will be going away from the asymptote. We need the domain, the range, and the asymptote. So the domain should be pretty easy. It's always going to be -infinity to infinity. It's always all reals. I'm going to skip the range and look at the asymptote. The asymptote's always going to be whatever's added outside. Again, nothing's added, so my asymptote's at y equals 0. I'm going to graph that. So there's my horizontal line at y equals 0. The range, since a is positive, is going to be above that. So it's going to get really close to 0, and then it's going to be above it, to infinity. Alright, now we need some points. An easy point is the y-intercept. The y-intercept means we're going to plug in 0 for x. If I do that, I've got 2 times 3 to the 0 power. So when you do the work, you're going to get y equals 2 times, anything to the 0 power is always 1, so 2 times 1 is 2. So my y-intercept is going to be at 0, 2. So I'm going to plot that point. So I've got that point. In all honesty, that's about all we're going to need, because I know that the right side is going to go away from the asymptote, and the left side is going to get really close. But sometimes it's nice to have a few more points just in case. So if I plug in 1 for x and do the work, let's see, I've got 2 times 3 to the first power. That's going to give me 6. So I've got another point at 1, 6. You guys can actually pick as many points as you want, using the table function even. But 1 point really should do it. And notice the right side is going away from the asymptote. That makes it a growth. Alright, take a look at the next one. I'm first going to rewrite this as y equals -1 times 2/3 to the x power. So you can really see what all the different variables are here. Since the number with the exponent is smaller than 1, it's going to be decay. Decay means that the right side is going to get close to the asymptote. I like to just make little notes. So the right side is going to be close to the asymptote. You can write more if you can fit it. Alright, the domain is going to be -infinity to infinity. Then I like to skip to the asymptote. Notice again, nothing has been added outside, so again my asymptote is y equals 0. Go ahead and graph that. Remember, your graphs should never touch that asymptote. Alright, since your a value is -1, it means that my graph is going to be below the asymptote, so my range is going to be -infinity to 0. But it's not going to touch 0, so you still need the parenthesis. Alright, let's get a couple points. Y-intercept, you plug in 0 for x. If you plug in 0 for x, you've got -1 times 2/3 to the 0 power, so that's just going to be -1. So I can plot the point at 0, -1. Another easy point is to plug in 1. It's not always going to be pretty. So 2/3 to the first power is 2/3. -1 times 2/3 is -2/3. So, not really easy to graph, but there's my 1 -2/3, so it's just a little bit below. Remember, the right side needs to get close to the asymptote without touching it. So there's my graph.